Welcome to Subatomic Tanvi.
Hi, everyone.
So today we are going to talk about this little thing here, right?
Uh, not really. That is a black body. We're going to talk about a black body.
Isn't that the same thing?
No, a black body is a theoretical object that absorbs all incoming electromagnetic radiation.
Okay, I kind of get that this is a theoretical object, but what exactly is electromagnetic radiation?
It's a form of radiation that travels through space. For example, if you turn on a light bulb, that light is a form of electromagnetic radiation. Or if you go to the doctor's office and see an X ray, that's a form of electromagnetic radiation too.
Oh, so what do black bodies actually do?
So, black bodies have some super interesting properties like perfect absorption and perfect emission of electromagnetic radiation.
Now I can see why this is theoretical.
Yeah. And it also depends on the temperature. The higher the temperature, the more the black body glows, just like stars, heated metal, and even molten lava.
Okay, so if the black body is a video game character and we give it more energy, it shines brighter?
You could think of it like that too.
Okay, so if black bodies have perfect absorption and emission of electromagnetic radiation, do they have their own radiation too?
Yes, actually. Black body radiation is what it sounds like, the intensity of radiation emitted by a black body.
Okay, can you explain that in a simpler way?
Okay, so imagine you're throwing a pebble into a lake. In the water, it makes ripples, right? So, just like that, electromagnetic radiation makes ripples, but instead of in the water, it makes ripples in the air, which transport energy. So, the more ripples, the more energy.
Interesting. I am glued to this topic now. Can you explain more?
Okay, so Max Planck discovered a formula that revolutionized our understanding of electromagnetic radiation. So let me just bring that up right now.
So, before you continue, a quick note to everyone. If you are listening to the audio of this podcast, just make sure you watch the video as well, either on Spotify or YouTube, so you can watch this presentation that Subatomic Tanvi is about to show. Let's go. Go ahead.
That's right. Okay, so this is the variation in wavelength across the electromagnetic spectrum. So first let's talk about this red side over here. So this side has a longer wavelength, a lower frequency, and lower energy, and we'll talk about why in a second. But first, let's do this purple side too. It has a shorter wavelength, higher frequency, and higher energy. Now, if any of you noticed, there are these sine waves at the bottom, and they're there for a reason. That reason is so here on this side, it has a shorter wavelength because the length of the wave or the wavelength is shorter, and it has a higher frequency because the sine waves make full rotations more frequently, and both of these factors add up to higher energy. And on the other side, it's basically the opposite almost. Longer wavelength because the length of the waves are longer, definitely longer than these tiny ones, and a lower frequency because it makes full rotations less frequently, and both of these factors add up to it having a lower energy. So that's it for the electromagnetic spectrum. But now let's talk about Planck's formula of black body radiation, which is this formula right here. Now let's dive deeper and see what everything means. So first, this part, B of lambda comma T, is the spectral radiance, or the amount of radiation emitted by a black body given lambda, which is the wavelength, and T, which is the absolute temperature. Here, this T is absolute temperature, this lambda is wavelength, and this whole thing is spectral radiance. And this C over here represents the speed of light. So here it would be speed of light squared. And here for the wavelength, it would be wavelength to the power of 5. And this E over here is Euler's number, which is 2.71828. This H is Planck's constant, discovered by the same guy who discovered the formula, Max Planck, which is 6.626 times 10 to the power of negative 34. Not 34, negative 34. So imagine how small, how tiny of a number that would be. And just like Planck's constant, this K over here is the Boltzmann constant, 1.380 times 10 to the power of negative 23. Again, a super duper small number. So that's it for Planck's formula of black body radiation.
This is amazing. An equation with so many constants. I love
Yeah,
quantum physics.
me too. Me too. Everyone should be loving quantum physics.
I agree. I do have one question though. How are black bodies relevant to quantum physics?
So, black bodies actually played a really important role in the birth of quantum physics. So, classical physics failed to prove anything at all about black bodies with all of their complex properties and its complex theoretical self. Classical physics failed to prove any of that. So, physicists definitely needed a new field, which is now quantum physics, that could prove all the amazing properties of black bodies and all about it.
Wow, that's great. Thanks for another fascinating episode, Subatomic Tanvi.
You're welcome. Bye, everyone.